Hey, welcome to Ones and Zeros. My name's Ben, and today we are taking a look at another one of our STM32 basics videos. In this one specifically, we're going to be taking a look at using the real-time clock peripheral in the STM32 devices. Now, let me just make sure that the stream is actually behaving itself, which it looks like it hopefully is. I guess we're going to find out. So we have just put out a video on using the random number generator peripheral. So if you're interested in that one, it's a nice short one worth checking out. So that one has just gone up on Twitch and YouTube as well as of a little while ago. However, as I mentioned, we're going to be taking a look at the real-time clock. So I believe nearly all of the STM32 devices have a real-time clock peripheral built into them, which basically allows it to keep track of time as well as what the date is as well. So the day of the week, what day of the month it is, what month and what year. So it can be quite useful, especially in situations where you may be doing data logging or things like that. This thing doesn't want to seem to behave itself for me at the moment, so let me just get that quickly fixed up. Technology's great when it wants to work properly. There we go, that looks a bit better. All right, so the one thing to be aware of with the real-time clock peripherals in STM32 devices is in order for you to get a nice accurate clock that is going to keep time correctly, you're typically going to be wanting to use a device that has a low-speed external oscillator on it. So whether you're using a development board or a custom board or something like that, that is the best way to make sure that you're not going to be losing time or gaining time or whatever based on real time. So if we jump over to this one, as we can see, we've got the STM32 F769i discovery board set up. This is the one we're actually going to be using today for the real-time clock driver that we're going to have a look at writing. And the reason for that is because it's one of the boards that does actually come with that 32.768 kilohertz crystal built into it. If we have a look at something like our, see if we can get the glare off that one, our typical Nucleo board that we've been playing with, light's not great on that one. Let's see if we can fix that up a little bit. So we can actually see right here, labeled X3 on the board, right near where my thumb is a hole for a crystal, which is not actually there. So that is where that particular crystal would go if it was going to be used as the low-speed external oscillator crystal. Now, if we have a look at one of my newer boards, which is the F429i Discovery board. Let's see if we can get that one in shot as well. You'll actually notice right about there, there's actually some empty pads as well. So this board also does not come with the 32.768 kilohertz crystal for the real-time clock, which, as much as I love STM32 devices, I do think is a little bit crap. I think that if ST had put a little bit more effort into making sure that those boards all had the low-speed external crystals, they could be a little bit more useful, because the real-time clock can be useful for doing things like time stamping if you're capturing data at regular intervals, as well as a whole bunch of other little uses. So you can look at soldering on the couple of capacitors and the crystal that you require onto the development board, or you can go with a custom board, or we can go with something like the F769i Discovery that we've got here at the moment that we're going to be working with. So let's just zoom in on that one a little bit, because this guy does actually have that crystal built into it. So that's why we're going to be looking at that for doing the driver for today. So that little rant out of the road, let's have a look at what we can do as far as getting the real-time clock up and running. And because this is a fairly simple peripheral to use, we're not going to look at actually setting up the peripheral the way we have with, say, doing our pulse width modulation and things like that, where we set it up in main CPP first. We're just going to get stuck into doing the actual driver, because we'll still be able to give a pretty good explanation of how all of the aspects of that are actually functioning in order for that to work. So first things first, going back to what we were talking about with the clocks before, if we just open up the MX file for this one, and unlike my last stream, I might remember to actually switch to the correct scene in OBS for this one. So once our device configuration tool actually decides to hurry up for us, gives me the opportunity to refill on a bit of coffee. All right. So if we jump into our clock configuration, we can see we've got our high-speed external oscillator, which is our main oscillator that's going to be used to drive the system, which is what's happening in the case of the way this board's set up at the moment. We also have our low-speed external oscillator, which, as we can see, 32.768 kilohertz. Now, there is also a low-speed internal crystal. However, the accuracy of this one is not going to be exactly 32.768 kilohertz, which means that if you set up the real-time clock using the low-speed internal crystal, you might find that the real-time clock may be gaining seconds over the course of a day. It might be losing seconds over the course of a day. So if you do choose to go with the low-speed internal crystal for that, just be aware that the time's not going to be quite as accurate. There's a reason why a lot of the older digital watches use 32.768 kilohertz crystals. It's because they do the job quite well as far as tracking time. So that's kind of the way that works. And then you've got the choice between, you know, which one of those you're actually going to use to be able to drive the real-time clock. So if we jump into our boot code here, so this is where we're actually getting our clocks and everything set up for this particular discovery board. We can see that we are turning the low-speed external oscillator on, which is important. And if we scroll down to where we're actually setting up our peripheral clocks, we're telling it that we want to set up the real-time clock, the clock source for the real-time clock. And we're also advising it that the real-time clock source needs to be the low-speed external crystal. So it's important to make sure that those particular parts are actually set up in order to make sure that you're going to get everything connected up properly the way it needs to be for that peripheral to work. So now that we've got the sort of clocking side of things out of the road, let's get into actually writing a bit of a driver, and let's start to see how that sort of thing actually functions. We do also have the random number generator driver here that we've just been working on for the previous video that came out just before. So if you're interested in how to generate some random numbers using that particular peripheral, definitely check out that video. However, let's get us some files created in here. So we're just going to call it qadrtc.hpp for our header. And we're going to go with qadrtc.cpp for our source file. let's grab the header from that one. We'll pop it over here. It's still the 18th of November. Change this over to RTC and RTC so that we know what those guys are. That'll be RTC as well. Same for that one. And we need our prevent recursive inclusion for the end of the file as well. And while I'm thinking of it as well, thank you to the new subscribers on YouTube. You guys are absolutely awesome. We are nearly, I think, one subscriber away from being 2/3 of the way to our 100 subscriber goal. I will just point out, once we get to 100 subscribers, there will be a little bit of a giveaway. One lucky person is going to score themselves a free microcontroller and potentially a couple of other bits and pieces to go with that, in order to have something to play with some code with. As we reach each of our sort of milestones that I set, there will be little giveaways and things like that, because I do want to share the sort of toys I love with the rest of the community as well. So definitely keep an eye out on our subreddit for that sort of stuff as well, which is r/ones and zeros, because there likely will be a bit of information going up there about that as we get a little bit closer to that as well. But we've also recently had over 100 hours worth of watch time on YouTube as of a few days ago, and we've had nearly 1,000 views in total in under 2 months since I started the channel. So again, thank you to absolutely everyone. That means a huge amount to me that you guys are actually enjoying the content. So now we've got those bits and pieces sorted out there, let us get a bit of a driver class written in here, and we're just going to call this QAD RTC, sticking with the naming convention that we've been using for most of our stuff up until this point. Pop a few lines down there so that we can scroll a little bit easier. We want a private section. We are going to want to track whether or not the driver is actually initialized. And we're just going to call that one ME init state. Stream seems to be behaving, which is awesome. We're going to need an RTC handle type def so that we can use that to access the HAL methods for this particular peripheral. We're also going to chuck in here a RTC time type def, which we're just going to call ms time, and an RTC date type def, which we will call ms date. Now, because we're going to be setting this up as a singleton class, because there is only one RTC peripheral in any of the devices, we'll set it up as a singleton class so that there can't be multiple class instances that could potentially clash with one another. If you've watched some of our previous videos, you'll probably have seen me use this particular technique as well. If you do find this a little bit confusing, I am looking at getting some videos done for our Unearthing C++ series coming up soon, where we will be starting to take a look at classes and singleton classes specifically as well. And sort of how they work and why we use them, things like that. So let's make our constructor for this one private, because that way it can't be called from outside of the class. We want to set our ME init state to not initialized, And we're also going to fill our handle all with zeros so that that one is all good to go. Now for our public section, we are going to need to delete our copy constructor and assignment operator. So for that, we're going to need to delete that one. So that is our copy constructor gone. And then for our assignment operator, we are going to want to, should be a constant, QAD RTC other, and delete that guy as well. Now we're going to have our singleton methods. So there will be our typical get method that we use in our singleton classes, which allows us to get hold of an instance to that singleton class. So just call that guy instance, and then that will return a copy of the instance. So because of the fact that we're defining this guy here as static, it means that it's going to grab the only one of that exists. As far as our actual constructor, that constructor will get called the very first time that the get method gets called. So that's kind of how that actual construction process occurs in essence. All right, so we're going to need to get some initialization methods sorted out. And again, if you're familiar with how we sort of approach the singleton classes, there'll be a bunch of static methods which then access our private implementation methods. So that'll kind of make a bit more sense as we get through and get those done. If you do run into any questions or anything like that as far as this sort of stuff, feel free to get in touch, leave a comment on YouTube, jump onto our subreddit r/ones and zeros, ask questions there, or there is also the onesandzeros.contact@gmail.com address as well, which you can contact us on. Which you probably would have seen at the start of the video and will come up again prior to the end of the video as well. So this one will return the result from our imp init method. So the static method is calling the implementation method, which we haven't defined yet. We're going to want a method to deinitialize it, which won't need to return anything. Like so. A couple of different approaches we could take with this, so just kind of figuring that bit out as we go. Now we're going to need some control methods. So first of those, let's just pop a line in there, will be a method that we can use to set what the current time is. And again, this one will be making use of the implementation method to be able to do that. So you're not sure what I mean by the implementation methods, just bear with me a little bit because we'll get to see those quite shortly. So to set the date, we need to know what day of the week it is, Monday through to Sunday sort of thing. We need to know what day of the month it is. We need to know what month itself it is, and we need to know what year it is as well. Now, as far as the year, it only stores it as a 2-digit value, rather than the full 4 digits. So, for example, if we were to store it as 2021, it's only going to store the 21 part. So, fully Y2K compliant, obviously. Makes me feel old saying that because I quite remember that and the very small number of errors that actually occurred as a result of the rollover to the start of the year 2000. So we're going to want an update method, and we'll kind of explain why we have this update method shortly as well. I just want to get the bulk of everything laid out, and then we'll go into a little bit more detail onto why we're doing certain things a certain way and how the driver will actually get used and things like that. So we're going to want to have some methods to be able to retrieve the different values of whatever the current time is. Now, we'll go with an implementation method for this one as well. We could go with a slightly different approach, but let's just do it that way. Now, we might also make another one of these where we can actually pass it a string so that we can retrieve the actual text for what day of the week it is, whether it's Monday through to Sunday. Actually, we might change the naming of that and get rid of that return value and do it this way. That should be a void in there. That'll fix that up for us. So we want one to be able to retrieve the the day of the month, which should be returning a uint8t. And that should be returning a value. I'm going to need one for getting the month. Again, that needs to return a value, so get month. Now we're also going to do one to be able to return the month string for that as well. That can come in handy. And lastly, we want one to be able to return what year it is. Which should also be returning a value. Alright, so that should be all of our static methods done. Now for our implementation methods. Now, I find it easier in this situation to get a split happening at the moment because we've got to match up some of our methods here with our actual implementation methods, so that way we can kind of see which ones we've got to do. So we've got our initialization methods where we want, that will be QA result imp init void imp dinit void. Then we're going to have our control methods. Now, if you've noticed some of the commenting that started to happen on the code that's going up on GitHub, all of this stuff will be more heavily commented as we move forward as well. It just kind of depends on time frames for me getting that sort of stuff done. But I have been going through and actually getting the code more heavily commented to make things a bit easier for beginners, and you know, if you're not sure what a particular thing is actually doing, then trying to provide better descriptions as to that sort of stuff as well. So that'd be uday, uint8t, umonth, and uint8t, uyear. Now we also want our update methods, which we don't need to pass anything to. And then we want our data methods. So for these ones, if we scroll down, where's my mouse gone? Scroll down over here a little bit, we can see those guys. So uint8t, imp get hour. Okay, so we're going to need get day and month. So we need the one to retrieve the string for the month, so we'll pop that in there. And lastly, one to be able to retrieve the year. All right. So now for the most exciting part of the whole lot. Let's just turn that split view off for that file there. And let's start getting these guys all laid out. I'll try and get through this bit as quickly as I can for you guys so that you don't have to sit through too much of the boring part. Although saying that, I actually find sometimes doing the code layout like this, I actually find slightly meditative, and it can actually be kind of fun. But I guess it depends. Especially if you're sitting there watching it on a video, maybe it's a little bit more boring. So why copy and paste tends to be your friend a little bit in this sort of stuff. As well as being good at keyboard control, I think that's something that's kind of important in the sense of kind of knowing where your home and page up, page down keys, things like that are, because the ability to jump between text and things like that can be great. The other one I love is being able to hold down control and use the arrow keys to scroll up and down without moving the actual cursor, and that way being able to scroll without even touching the mouse can be super useful. Okay, and these will be data methods. And that one there. Now the other thing that we've got coming out soon too is a series of videos on viewer questions. So we have had a couple of people asking questions. Apologies for not remembering names off the top of my head, but I think it might have been Wolfson on Reddit who was asking about doing UART pass-through, which we're going to take a bit of a look at, as well as... Apologies for not remembering your name, but the person who left a really lovely comment on YouTube asking about sort of why it's so hard to get information about what the DSI peripheral is and how it works and all of that sort of stuff. So we're going to have videos coming up on those in the near future. So if you do have any specific questions or anything like that that you'd like us to focus on, definitely feel free to leave those questions for us, because especially if it's something I find interesting, especially as far as like explaining what DSI is, how it works, and sort of the dark art behind it that seems to be difficult to get information on. I'm more than happy to put together some stuff and try and make a bit more sense of it for people, because if you've got a question, chances are someone else somewhere is asking the same question. So I don't consider any question to be a silly question. The only silly part is not asking the question and not knowing in the first place. So if you're not sure, definitely ask. All right, so looks like we've got all of those laid out. So let's start with getting our actual initialization of the peripheral done. Now, this is a fairly simple peripheral to get set up and actually working. There's a lot of methods there that we've actually gone through and chucked in there, but overall, the driver itself is a fairly simple thing. So first things first, to initialize it, is we're going to need to enable the clock that drives the RTC. So in the case of what we were talking about before, that'll be the low-speed external crystal that we're using on this board. So we're going to enable the RTC clock, and then we're also going to enable the RTC itself. Actually, we might do that. No, we'll do both of those together. That's normally the approach I would take, so we'll stick with that because we know it works. Okay, so now we need to initialize the peripheral. This, we're going to fill out some details in our handle structure. So first up will be our instance, which will be RTC, because that's the peripheral we're getting set up. Now there's different hour formats that you can go with. So you can select to go with 12 or 24-hour format. In this case, we're going to go with 24-hour format. It's kind of up to your own discretion which way you want to go with that. You'll notice that there is the option there to go with 12 as well if you choose to. But for the moment, we're just going to go with 24. Part of the reason why I do it that way is because it's not super difficult from a programmatical perspective to actually convert 24-hour format to 12-hour format, or vice versa. So depending on, like, if I'm doing something where I'm doing timestamps, doing data logging of a particular thing that I've designed a device for, I generally find it easier going through the timestamps looking at 24-hour time rather than looking at the whole AM and PM thing. But again, comes down to personal preference. Okay, so our async pre-divider will be 127. And our sync pre-div will be 255. Missing a H there, that would help. It's always good if we spell these things correctly. So we jump back into here. We can see that the pre-divider values, as far as my understanding of them, and I could be wrong, do help determine the actual tick rate based on the incoming clock to the RTC. So in this case, the 32.768 kilohertz or 32,768 hertz value, those allow it to then function at the correct timing. Now, I could be wrong about that, but that's my understanding of it at this point. So feel free to correct me if I've got that mistaken. Okay, so I'm going to go output disable for that one. There is different timers and alarms and things that you can also set up with the RTC. We're not going to worry about any of this in this particular video. We might have a look at that in a future video. But for the moment, we're basically just going to get the clock up and running and sort of show you how you can actually start to make use of it. Now, our polarity here is not going to matter too much because our output's disabled, but we'll chuck that in there anyway. Part of the reason why I put like our output polarity and output type in here is so that if I copy and paste this code to something else for another project, then that stuff's there in case I do want to be able to make use of it, rather than having to try and figure it out. So let's get our RTC initialized. So for that, we're going to pass it a pointer to our handle structure, and we're going to check whether or not it's succeeded. If it hasn't succeeded, then we are going to disable our clocks. Now, part of the reason for this is so that it fails gracefully, so that if the initialization fails, our peripherals are in the same state that they were in before we tried to initialize them, which is something that, especially as we head towards trying to do things a little bit more dynamically, is kind of important. So if you've watched some of the previous videos, you'll realize that kind of my end goal in some ways is to end up with what is essentially a cut down version of an operating system that we can use across various STM32 devices, including allowing those devices to be connected together to become a larger system, which will be what is going to get known as Quartz Arc OS. So the goal of our approach to a lot of the drivers at this point, and the way we're doing them as classes and making them more dynamic and more able to fail gracefully, is simply so that, make sure I type that correctly, is simply so that when we go to start doing things more dynamically, we are not going to run into issues if we're dynamically allocating peripherals and things like that while the system's running. So rather than having things hard-coded, we can have things so that, say the system's been running for an hour and there may be a particular task that starts up on the operating system that goes, okay, I need access to be able to control a couple of servos via PWM. I need a particular timer that's got PWM capability and the channels that I need to be able to do that and the GPIOs to do that. And it can just set that up and make that work. And then when it's done with it, it can deinitialize that and everything's back to the way it was before any of that happened. So it's important to make sure that it's much like in C++, making sure that if you are sort of setting up or allocating memory dynamically using malloc or new, that you are then using the respective free or delete operators in order to make sure that you're cleaning up after yourself so that you don't get memory leaks or things like that. That's kind of my explanation for that, I guess. Hope that makes some sense. Okay, so as far as our deinit method, we first want to deinitialize our RTC peripheral. Now, deinit in the HAL has a capital I, so we'll make sure we pop that in there. So deinit RTC peripheral and disable clocks, which will be our HAL RTC disable and our HAL RTC clock disable, like so. Now, because we're also tracking whether or not the driver is initialized, which is why we've popped in our QA init state or a ME init state here, we also need to be making sure that that's getting used as well. So we're going to, at the top of our init method here, we're going to check if it's actually initialized, because if it is, then we're just going to return QA OK, because it's already initialized, it's already good to go. Much like if we go to call the deinitialization methods and we're already deinitialized, there's no point trying to deinitialize again. So again, if it's not initialized, then we'll just return rather than actually trying to go through and do that deinitialization. Now, as far as setting our time, we're going to make use of the RTC time type def and RTC date type def structures that we've put in the driver for this stuff. And there's another reason why we're going to be using these as well. So we're going to have a look at that in a moment. So that'll be U hour, MS time, minutes, minutes, MS time, seconds, equals U seconds. Now there is also our second fraction, which we're just going to set to 0. Now we're also going to set daylight savings. You can enable daylight savings if you like. We're not going to worry about that for the moment. I live in Queensland. In Australia, we don't do daylight savings here, so that's my excuse for that at the moment. We get plenty of daylight up this way. And our store operation, we want our store operation to be reset. All right, so that's got that filled out, and then we can go how RTC set time, pass it a copy of the handle, pass it a copy of the time type def structure, and we're going to tell it that the particular format that we're using to store that data is binary format. It can also do binary coded decimal. However, I typically always, with my projects, just go with binary. Binary makes more sense in my head, so if that has failed, it'll return QA fail. Otherwise, if it's succeeded, it will return QA OK. Now, as far as setting our date, that's going to be fairly similar. So go MS date, weekday will be U weekday, MS date, and date is effectively the day of the month. And then we've got month, which will be U month, and year, which of course will be U year. Now, in this one, I don't believe we've got any other details. No, so it's just those 4 details we need to fill out. So the store operation and daylight savings and stuff is just for our time structure specifically. And then we can just go how RTC set date. Again, pass it a copy of the handle for the peripheral, pass it a copy of the date type def, and again we want to tell it that we are using binary format rather than binary coded decimal, like so. And if that fails, we're going to return QA fail, and if it succeeds, we're going to return QA OK. All right, now onto our update method. So the reason why we have an update method is so that, say if we are capturing a timestamp, so say in the event of one of my previous projects that I worked on where I was developing a ceramic kiln controller, so to control the heating elements based on set temperature for basically taking raw clay and turning them into ceramic products. It's a project that I'm still kind of working on for a good friend of mine. So for that one, there needs to be basically a log of all of the data from the various temperature sensors, from, you know, whether that certain heating elements are on, what the system's doing at that sort of time, even monitoring things down to the CPU temperature. And those timestamps need to be taken at regular intervals. So firstly, we're using the real-time clock to trigger those intervals because it's going to be slightly more accurate, say on a per second basis, than using a traditional timer. But it also means that when it's time to take that snapshot we call imp update, it then takes a snapshot of what the current time and date values are in the real-time clock and holds on to them so that I can then access those and store those out with the rest of the data. So that, say if it took, unlikely, if it took 10 seconds to be able to store all of that data and we were gathering bits and pieces of the time there, we're not going to end up with the timestamp looking weird where the seconds may not be what they were when we first triggered that timestamp. So what update does is it basically takes a snapshot of the current time and date that's stored in the real-time clock that we can then access using our other methods below, like get hour, get minute, get second, etc. The other part of the reason why we do it that way is because of a particular quirk of the way the real-time clock works. Now, I'm just going to copy and paste this bit of code over here, just to save us that little bit of time. So, if we take a look at the HAL method for getDate, it does say here you must call HAL RTC getDate after HAL RTC getTime to unlock the values in the higher order calendar shadow registers to ensure consistency between the time and date values. So the other reason why we're using the update method is because it does get time, then it does get date, which means that not only are we getting a copy of those values, but it's doing it in such a way that is actually going to work for the peripheral and for the HAL driver so that we're not going to run into any issues. So basically it's storing the current time and date at that moment into our time and date type defs, like so. Now, what we're going to get on with next is getting the last of our methods here sorted out, and then getting things tested, making sure everything's working correctly and that we can actually get some time. We'll see if we can get some time showing up on the actual LCD screen as well as via our serial monitor. But prior to that, I am just going to take a quick bio break and I will be right back in a few minutes. All right, so we are back. Alrighty, let's get these methods finished off. So, first ones are going to be fairly easy because we're just going to return ms time hours. This one's just going to return ms time minutes. And ms time seconds. As far as this one, that's just going to return ms time. No, that'll be ms date. Make sure we get that right and spell it correctly is probably a good start. That'll return the weekday. Now, as far as this one, this is where it gets a little bit more interesting, because we need to be able to make a determination of what the weekday is. So let's go for a switch statement, and we'll use ms date weekday for that. Go case and I believe it's 1 through to 7 that these are indexed, so let's go with, do we have string.h in here? I don't think we do. Let's just pop string.h in there just so that we can use string copy. So Monday and then break. Seven of those. Mix up the numbers for these guys. 5, 6, and 7. Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Makes it nice and easy. Now, as far as this one, this is also a fairly easy one because we can just go return ms date. That'll be date. This will be another simple one because we can just return ms date month. And then we're going to need to do another switch statement in here for this one based on ms date month. And again, these ones are indexed 1 through to 12. String copy to string month January, and we'll want a break statement in there. Get my indents the way I like them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those. Make sure they're indented the way I like them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We're already down here, so let's start here. December, November, October, September, August, July, June, May, April, March, which is the most important one because that's when my birthday is, and February. Alright, so that's those done. Now what we might do with year, just to make things format slightly nicer, we're going to change this to a uint16t that actually returns, which means we're going to need to change that over here as well. And we're also going to need to change that in here as well. And the reason for that is because I can't see this code being used past the year 2099. So for our year, we're actually going to return ms date year plus 2000. So that way it's going to give us the actual full 4-digit year. It's not Y3K compliant, but that's fine because we can live with that anyway. So that is all looking fairly good at this point. Let's see if that wants to build for us. No, some errors, of course there's errors. Wouldn't be one of my streams without some errors. Okay, so what do we got here? Yep, can't spell. That's always a good start. What do we got down here? Really? I'm just going to change that there, and we'll change that over, where's weekday, weekday. Let's remove the capitalization from those guys. And let's build that. I'm guessing we're still going to see an error there. Yes. What are you complaining about? Okay, so that one should be capitalized. No other errors that I'm spotting there, so I'm guessing that's all of them. Let's find out. Three warnings. What are our warnings? Okay, there should be a return in there. That would probably help. And what are you complaining about? If clause does not guard. Okay, well let's chuck some curly braces in there, and that way you're not going to complain about that. And we should have 0 errors, 0 warnings. Beautiful. Alright, so we have a driver working. So let's jump into our main CPP. Now, we were using a thing to update our random number generator stuff for the last stream, so I'm going to keep that in there so that anyone that wants to check out the code from that can do so. So we're going to do sort of something similar for the real-time clock. Now we're going to need uint32t urtc update ticks equals 0. Okay, so if you RTC update ticks plus equals uticks, if you RTC update ticks is greater than or equal to QAFT, RTC update tick thresholds, then we're going to need to clear that again, so we'll subtract away RTC, that should be RTC, update tick thresholds, and we're going to use our same string out that we were using before. So how shall we format this? We'll go, where was the page I had open? Let me just find the particular reference I want for this. I wish I could remember all of the printf stuff off the top of my head. Okay, cool. So we're going to want 2u followed by 2u followed by 2u for that one, and let's get QAD RTC. Might help if we include QAD RTC in here as well, otherwise it's not going to know what we're talking about. The other thing we haven't done is actually initialized it, which we will do down here. So init RTC driver, and it's going to cheat a little bit and replace RNG with RTC for all of those, rather than having to retype it. Solves that problem nicely. Okay, so if I now go across here, we should be able to go get our QAD RTC get minutes. Might help if I put the parentheses in there, and QAD RTC get seconds. Okay, that works, and then we will print that out via serial. And just test it to make sure that we are getting something that is actually regularly ticking. That should have an S on the end of it. Again, spelling, sometimes it's useful. At least the compiler seems to prefer it if the spelling's done right. Let's pull up our serial thing here. We'll clear that. And let's see what we get. something not quite right happening. Oh, I know why. It's because we are not calling our update methods. So it's not updating the data. So let's just call that update method. We will re-upload that code and we should be getting some there we go. So we can see it's ticking through the seconds. Now, because we didn't call set date or set time, it's basically just started with its default values. And the thing is because the real-time clock operates on the backup domain, even if we reset the device, so if I hit the reset button right now and it reboots, it's going to carry on from where it left off, which is one of the really cool features of the real-time clock, is even if the CPU restarts, it's still going to continue on ticking in the background anyway. So as we can see, this keeps on going from where it was at, which is really good because if you design a device where you've got your VBAT supply separate to your main power supply for your STM32, as long as VBAT is continuing to get power regardless of the rest of the chip being powered up or not, the RTC and the backup domain is still going to hold the memory that's stored in it, and the RTC is still going to continue ticking the way it should be. So that kind of gives us a bit of an idea of how that kind of works. Now, what we may as well also do, one last thing while we're here, just because we can, is rendering this stuff to layer 1. So let's copy and paste this, because it's one thing to get that data being displayed on let's go with that font. So we'll clear that layer, and then let's print that same string to there. So again, just using some of the LCD rendering methods. And let's see if we can actually get to that time being displayed on the LCD screen as well. So we'll pull up the serial monitor again as well. Just clear the data out of that one. Okay, and if we jump over to this one here, we can see we now have the time being displayed on the LCD. So, and then if we jump to this one, you can see that we're getting it both on the LCD and serial all synchronized. So that is how the real-time clock works. Like I said, there is a few other features like the alarms and certain things like that, which we haven't gone into, but we'll take a bit of a look at those in a future video. I do hope that you've found that one nice and interesting, and that there may be something you've learnt there. If there's any questions, as I've mentioned previously, feel free to leave them in the YouTube comment section. Feel free to jump onto our subreddit, that one there, r/ones and zeros. Definitely happy for anyone to leave feedback, comments, things like that there. You can also get in touch with us via onesandzeros.contact@gmail.com. Again, the code from this video will be going up onto GitHub probably in about 10 minutes time. So feel free to have a bit of a play with that. The code is free for personal use, so if you want to use it on any of your personal projects or mess around with it, things like that, that's perfectly fine. However, it is not free for commercial use. If you do want to use any of the code that is being developed for QuartzArk for commercial purposes, then you need to get in touch with us via the onesandzeros.contact@gmail.com address, and we can potentially discuss licensing options. Can't go into too many details about why that change happened, but as I've mentioned in other videos, I would love to be able to give all of the code away for free. But at the end of the day, bills need to be paid and food needs to be put on the table. So, yeah. If you do want to help the channel moving forward as well, as far as it helping to improve the streaming setup, getting more cool toys to be able to mess with and show you guys how to use, there is also the Patreon down there. When we start to do some of the QuartzArk OS stuff in the videos, although those videos will be available to everyone, the actual code for the OS side of things will only be available to top tier Patreon members. However, a lot of this lower level driver style stuff we will still be continuing to make free for everyone, again on a non-commercial basis. So hope you've enjoyed that. Hope it wasn't too boring, and clock's ticking, so I will leave you with it. Hope you have a wonderful night, day, morning, evening, whatever it is where you are in the world, and thank you so much for watching.